Guys, we're going to look at ohmic conductors and non-ohmic conductors, starting off with an ohmic conductor. What this means is that it follows Ohm's law, which is this relation here, V is equal to IR. So if you have a graph of current against potential difference, voltage, you'd get a straight line, and that straight line represents the resistance. So remember that the gradient of this straight line is resistance. So an ohmic conductor is one where resistance is constant and one that follows this law. Let's look at what happens when resistance is no longer constant. So for example, a filament lamp. A filament lamp is non-ohmic because the resistance is not constant. Even though there's a straight line here which represents some proportionality, it kind of tails off at the edges. We're going to explain why that happens. So for a filament lamp, you're going to get an increase in heat because of the electrical energy being transferred to heat energy. And that heat energy is going to cause more vibrations, which makes it difficult for the electrons to move, to get through the resistor. And in our experiment, once we start increasing our current, there's more temperature, so there's more transfer to heat energy. And this increase in current, which causes the increase in temperature, will mean an increase in resistance because of the increase in vibrations, which therefore means a decrease in current. So to summarize, you get an increase in heat from the vibrations. In our experiment, as we keep increasing the current, there reaches a critical point at which that increase of current is going to increase the temperature so much so that the resistance will cause an effect and decrease the current. Hopefully that makes sense. So remember, a filament lamp is non-ohmic. Okay, so now let's move on to a diode. A diode is another example of a non-ohmic conductor. You can see this is the graph, current against potential difference. It kind of stays constant for a bit and then it hits about 0.6 volts and then shoots up, right? So this shooting up is when it actually starts to conduct. And this flat line here is because of incredibly high resistance. And that's what a diode does. It's in one direction, and it only really flows in that one direction for what we need to know now. So yeah, this is in a forward direction. Remember the symbol for a diode. It was like a circle, and then it had like a start, stop, and then a line through it. That's what this is. That's a graph to represent what's going on. Okay, now a few applications of these things. A few applications of actually LDRs and thermistors, which are non-constant. I haven't drawn a graph of them because for our exam we don't really need to know a graph. But for an LDR, we use them for light-sensitive circuits, and for a thermistor, we use them for like temperature regulation stuff. They're incredibly accurate and sort of predictable, so they're kind of useful for what we need. Yeah. So I want you to try out these questions. So first of all, what is an LDR circuit? Is it A, B, or C? Okay, hopefully you've unpaused the video now and noted that indeed an LDR is A because it's light dependent. Arrows coming in, remember, depends on the light. Okay, question 2. If the resistance of an LDR decreases, what happens to the light intensity? Will you have low light or will you have high light? Pause the video. Okay, so you're gonna have highlights because remember, when the resistance decreases, the light intensity increases. When the resistance increases, your light intensity will decrease. And this, unfortunately, I've already drawn it here, is the circuit for a thermistor. So yeah, to draw this is just a recap. Then this is the symbol for a thermistor. Anyway, hope that helped. If not, let me know what I'm doing wrong, and hopefully you'll use the photocopy of this for some revision help. Anyway, thank you very much. Bye, guys.